All right, so the first type of weak base is a neutral chemical that can accept a proton. Okay, so we got an example right here in ammonia, not ammonia, but ammonia is a very good example of it, NH3. Another one right here is CH3NH2. That is another example of a weak base in this category. So we have one example. NH3 is a good example of a weak base in this category, and another example is right here, CH3NH2. I think this is hydroxylamine. I don't think it's hydroxyl. Never mind. Okay. And so you guys can see that it can accept a hydrogen and turn into this compound right here, CH3NH3. You guys see that? That's going to be one type of weak base. Okay, so if we wanted to answer 12.39, this molecule right here, we're going to say that it's this is C. Oops, dang it. I'm out of my mind today. This is C, this is H, this is H, this is N, and this is H. Okay. I want you guys to write down, just maybe somewhere on your paper, which one of these atoms accepts the proton. In this compound, which one of these atoms will accept the proton? So we got CH2, NH. Which one of these will accept? All right. Any thoughts? Who do you think will accept the proton? Yeah, the nitrogen. So the nitrogen will accept the proton. That's pretty much it. So if you guys notice, in these types of weak bases, a lot of times it's there's a nitrogen with non-bonding lone pair electrons, and that's the one that's going to accept the proton. Nitrogen is pretty good at accepting protons. Okay. All right. Any questions on the first type of weak base? Okay. Let's move on to the second type. Okay, the second type of weak bases are the anions of weak acids. Okay, so for example, we have this compound right here. This is a salt. Okay, NaClO, and it can break down into Na plus and ClO minus. Okay, so you guys should see that Na is a spectator ion because it's just an ion. But then this is the conjugate base. ClO minus is the conjugate base of a weak acid because we can have HClO. HClO can also turn into ClO minus. And so this right here is a weak base. Okay, because even though it came from a salt, even though it came from a compound that's not an acid, it's still the conjugate base of a weak acid. Does that make sense? So basically here, we get ClO minus from a salt, but we can also theoretically get a ClO minus from a weak acid. There's two equations that can actually take place to make this. We can either use a salt, or if we had a weak acid, HClO, it can go into equilibrium with H plus and ClO minus. So there are two different ways to get ClO minus. And since ClO minus is the conjugate base of a weak acid, doesn't matter where we get it from, it's still going to be a weak base. It doesn't have to come from a weak acid. Okay, so let's say, for example, I had a container, okay? And inside the container, we put in NaClO, and then what would happen is it would break down into Na plus and ClO minus. The point is, even though I didn't add an acid or a base, right? ClO minus is going to act as a weak base. And so you can see this right here. It's going to interact with the water to go into equilibrium, and it's going to produce its weak acid conjugate, HClO, and it's going to be a weak base. Okay, and so even though I didn't put an acid or base into the solution, because the ClO minus is the conjugate of a weak acid, it's going to produce a basic solution. Okay, hopefully that makes sense. Okay, so you don't need to add an acid or a base to make something acidic or basic. If one of the ions is a conjugate, it could still turn it acidic or basic. Alrighty, so with that being said, we're gonna go straight into an ice table problem. I'm gonna kind of throw you into the fire right here. Okay, let's go into 12.40. Okay, so here we have a solution that's made by adding NaClO to enough water to make 2 liters of solution. Okay, so basically what it's saying is that we got a container, same thing as before. We're gonna put NaClO into it, and then the volume is gonna be 2 liters. Okay, and the pH ends up becoming 10.5. Okay, so using the information from the equation here, this is the equilibrium that gets set up. We want to figure out what or how many moles of NaClO were added to the water. So like we said, the NaClO is going to break down into Na plus and ClO minus, and this ClO minus right here is going to go into equilibrium with water to produce some acid and stay as base as well. Okay, does the scenario make sense? What we're trying to figure out. We added some salt, NaClO. It breaks down, it breaks down into Na plus and ClO minus, and the ClO minus inside starts reacting with the water, and then it could turn it to the weak acid. Oh my gosh, sorry, something in my throat. It could turn into HClO or OH minus. Okay. All right. So what we're gonna do is we're gonna start by setting up our ice table. Okay. So make sure you guys copy down the equation and write your ice table. Now, if we think about what we're looking for moles of NaClO. Okay. Now, if we think about this, NaClO breaks down into Na and ClO minus, right? There's a 1-to-1 relationship between the moles of NaClO and the moles of ClO minus, right? Because if we write the chemical equation, it's going to look like this. It's a 1-to-1 ratio. So if you can find the moles of ClO minus, that means you can find the moles of NaClO. Does that make sense? Okay, so what that means is if you look on our ice table, what we're going to be looking for is this right here. We're going to be looking for the initial concentration of ClO minus. Okay, because if I can find the concentration of ClO minus, that's going to be the concentration of NaClO, right? Because it's going to be 1-to-1 ratio. If you look right here, it's just 1-to-1. So whatever number this is going to be equal to the moles of NaClO, which is what we're looking for. Okay. All right. So let's start the problem. So we're going to be working backwards for this ice table, because if you look at the information we're given, usually it's asking us to find the pH, right? But we already start with the pH. The pH is equal to 10.5. And so whenever we're looking at the pH, we're talking about the equilibrium conditions. Okay, so whatever information we get from the pH equation, it's going to go into this bottom row right here. Okay. Now we can take the pH and we can turn it into POH, because we don't have anything about H plus, and pH is all about H plus. Okay. So the POH is equal to 14 minus the pH. And that's going to give us an answer of 3.5. So I'll give you guys a second to copy that down. Kind of just think about it. If you have any questions on what we're doing, make sure you let me know. So far, so good, guys? Make sense? Okay, so we know that pOH is equal to 3.5, but we also know that pH is equal to the negative log of the concentration of OH minus, right? And so if we can find the concentration of OH minus, we can plug it in right here. Okay, so what I want you guys to do is take about maybe 40 seconds. I want you guys to use the pOH to find the concentration of OH minus, and that's going to be the number that we put on the bottom right. Okay, let's take a second to do that. Alrighty, guys. So in order to do the calculations here, you would just have to do 10 to the power of negative 3.5. And so that should give you a concentration of 3.2 times 10 to the negative 4. Everyone got that? Okay. So the value, the concentration of OH minus right here is going to be 3.2 times 10 to the negative 4. Okay. Yeah. Sorry, what was that? Because pOH is equal to negative log of OH minus. So you need to move the negative before you can put it to the power of 10. Yeah. Any other questions? Okay. Now that we have that, we can start filling out more of the ice table. So we know that we don't care about pure liquid, so I'm just going to put dashes here so we don't need to worry about it. Okay. And then we know that in the beginning, if we go back to the beginning of the scenario, there wasn't any HClO and there was no OH minus, right? Because all we had was ClO minus. So we started with 0 and we started with 0. Okay, which means we started with some value for ClO minus, but then some of this decomposed, right? We lost some of that. And then that means we gained some amount of HClO and some amount of OH minus. Now, you should be able to see that if I started with 0 and I gained X and I got 3.2 times 10 to the power 4, that means we know that X is going to be equal to 3.2 times 10 to the negative 4, right? Because that's how we go from 0 to that. So what that means is since HClO also gained the same amount, we're going to have 3.2 times 10 to the negative 4 here. And since we lost, right, we lost some amount, that means that the amount that we lost was 3.2 times 10 to the negative 4. Okay, because the concentration of OH, if we started at 0, the change was 3.2 times 10 to the negative 4. So that means the change for everybody else has to be that as well. Okay. Make sense? All right. Okay, so from there, we can just use the equilibrium constant equilibrium constant equation. We can do Kb is equal to the concentration of the products divided by the concentration of the reactants okay. And we know that that value is equal to 3.3 times 10 to the negative 7. So I don't like using the question mark, so I'm just going to put y as the value. Okay, so we'll just change everything to y. So we'll change the question marks to y. And so what I want you guys to do is I want you guys to calculate y using this equation right here. So we can replace the concentration of this with 3.2 times 10 to the negative 4. So up here, we'll have 3.2 times 10 to the negative 4. Since we have it twice, we can square it. Okay. All right, so I'll give you guys about maybe about a minute and a half to calculate for y. I want you to remember when you can use the 5% rule. And so you can use the 5% rule because the exponent is less than 10 to the negative 4. So a little help there. So use the 5% rule. You can ignore the change. And then you guys can calculate for y. Okay. Alrighty, guys, let's go over it. So we said that we can use the 5% rule because the KB, the equilibrium constant, is less than 10 to the negative 4. So we can basically just ignore this right here. Okay, from there it becomes a very easy calculation. We just need to multiply y on both sides. So we can get y right here. So I got this equals to that. And then from there, we just need to square the 3.2 times 10 to the negative 4. So 3.2 times 10 to the negative 4 squared should be equal to 1.024 times 10 to the negative 7. And then the only thing that we need to do is isolate the y. So we can divide both sides by 3.3 times 10 to the 7. That should give us a value of y is equal to 0.31. Okay, so what that means is the initial concentration of ClO minus is going to equal 0.31. Okay, so this is the concentration of ClO minus. Okay. Remember, 5% rule means that you can ignore the change. Okay, we're not done yet because we have to figure out exactly what the question is asking for. And it's not asking for molarity, it's asking for moles, right? We said that the concentration of ClO minus is equal to the concentration of NaClO. So what we can do is we can plug this into the molarity formula, and then that'll let us finish up. Okay, so the molarity, if we're looking for moles, that means we can rearrange this as molarity times liters. We have 0.31 molarity, so we got 0.31 molarity times the liters. We said it was the volume was 2 liters, and so we're going to get a final answer of 0.62 moles of NaClO. Okay, so if you add 0.62 moles of NaClO into a solution, it'll make it into a solution that has a pH of 10.5. So even though you didn't add any base directly, it still made the solution basic because one of the ions, ClO minus, is going to react with the water. Okay. That was a long problem, huh? What a great way to start the day. Nothing like a ice table problem to get you up in the morning or put you back down. Yeah, what's up, Great? How I got y? Yeah, so we had the KB equation, and so originally we had the fraction where we had this guy on the bottom, right? So all I needed to do was multiply both sides by 3, or I had y on the bottom. So all I needed to do was multiply both sides by y. So if I multiply both sides by y, this fraction disappears, right? Because if I multiply by y, they cancel out. And then I'll get y on this side. And I just did 3.2 times 10 to the negative 4 squared. That gives me 1.024 times 10 to the negative 7. And then we would just divide both sides by 3.3 times 10 to the negative 7. And that's how you get 0.31. So the math is 3.2 times 10 to the negative 4 squared divided by 3.3 times 10 to the negative 7. Yeah, so we can ignore the change. Originally on the bottom, we had this right here. But if we use the 5% rule, we can ignore this part, the change. Answer your question? Any other questions? Yeah, I know there's like so many little things that go into this. Now we're pulling in the molarity formula from back in the day. So yeah, it's a lot of stuff. Alrighty, ready to move on, guys? You're like, please move on. Okay. I'm going to give you guys about 5 to 7 minutes. I'll give you 7 minutes. I want you guys to try this problem right here. Basically, the same thing. I want to help you guys out a little bit by giving you the equation, though. We have NH3, and then we said NH3 again is a weak base. Okay, so when it reacts with water, what it's going to do is it's going to leach a hydrogen from the water. So it's going to turn into NH4 plus, and then it's going to produce OH minus. So that's the equation. And what I want you guys to do is, using that equation, I want you guys to figure out the molarity of the NH3 solution. Okay, if the pH becomes 11.17. Okay, I'll give you guys about 7 minutes to try that out. Feel free to work with the person next to you. Alrighty, guys. So I'm gonna start going over the problem. If you guys are still finishing up, please feel free to do so. And you can just check your answers at the end. But I'm gonna start going over the problem. Okay, so this is basically the same problem as earlier. We start with the pH. And so what we're going to do is we're going to convert that into the POH. So if we convert this into POH, we should get a POH that's equal to 2.83. And then we know that that is equal to the negative log of the concentration of OH minus. And so if we solve for the concentration of OH minus, we should get an answer of 0.00148 molarity. Okay, so we can plug that into our ice table. So OH is going to have an equilibrium concentration of 0.00148. Okay. And then we said earlier that we start with no conjugate acid and no OH minus. So same thing, we're going to gain an X amount. And so the amount that we gain is going to be 0.00148. So what that means is I'm just going to replace the X's. If you guys, your ice table looks a little bit different, that's fine. What really matters is the equilibrium concentration. It just means that we gain 0.00148 for both of them. Okay, but if you kept it at point or plus X, that's totally fine. And then we lost 0.00148, and then we'll say that this is Y. Okay, so Y minus 0.00148. Okay. Now we're looking for the molarity of aqueous NH3. So that means this Y is the answer that we're going to be looking for. And so what we are going to do is we're going to be using our KB in order to solve for Y. So my KB is equal to 1.8 times 10 to the negative 5. It's equal to 0.00148 squared on the top divided by Y minus 0.00148 on the bottom. Now, if we look at the KB value, it's less than negative 10 to the negative 4. So we can just ignore the change. So we're going to ignore this right here. And then from there, it's a very simple calculation. We just need to square the top. And so if I wanted to kind of rearrange this, I would square the top. And then I would just replace the 1.8 on the bottom. Times 10 to the negative 5. And that's what Y is going to be equal to. Okay, and then from there, you just need to solve for Y. So this is a math calculation you will actually be doing. Okay, so you'll get a value of 0.123 molarity NH3. Okay, and here we don't need to do anything fancy for moles or liters. We just need to find the molarity, and so that's going to be your final answer. So a bit easier than the other problem. All right, any questions? Hopefully not too bad. Okay, again, just get very comfortable with the ice table concept. It's very useful for the problems that we do. Okay, let's move on to the next topic. So I'm going to skip this part right here. This kind of review, so I'll skim it real quick. Basically, if you multiply the Ka and Kb, you get the Kw. It's always going to be 1 times 10 to the negative 14. We've talked about this. We also talked about if you have an acid, a strong acid, the conjugate is going to be a weak base, and that's kind of how the relationship goes. We're not going to be doing these problems. Basically, you just have to use this equation right here to find the Ka or Kb. Okay, but this is the important part right here. Acid-base properties of salt solutions. We've kind of done this already. We talked about how if we add a salt, it can turn a solution acidic or basic based on the ions that's produced. It's a lot of words. Basically, what we were saying earlier if you put a chemical inside of a fluid, right? Any space for a picture. Okay, like we said earlier, if I have a compound that's a salt, so we had one earlier. What was it again? Thank you. NaClO. This is a salt. If we put it in a solution, it can break down into Na plus or ClO minus, and that's going to make it either acidic or basic because of the conjugate acid or base. That's basically what all of this text is telling you, if I can just summarize it, okay? It's going to either turn it acidic or basic. Okay, does that make sense? Okay, and based on that property, we can figure out what the pH is. We can talk about the acid and base concentrations in there, okay? Okay, so what we're going to do is we're going to move on, and we're going to talk very briefly about how anions react with water, okay? So we know that if we have an acid, let's say we have HX, it's going to break down into H plus and X minus, right? Now, depending on what type of acid this is right here, it's going to affect the strength of this conjugate base. Okay. We said the stronger the acid, the weaker the conjugate base, right? That's kind of the relationship that we know about. So if HX is one of the strong acids, those are the ones that go to completion. They just break apart completely. Okay. It means that the conjugate base is a spectator in acid-base chemistry. Basically, it doesn't do anything. So let me give you an example of that. I'm going to pull up a notepad real quick. Okay, so let's say, for example, let's look at HCl. Okay, we know that HCl is a strong acid and it breaks down into H plus and Cl minus, right? Okay, now there are some salts that contain Cl. So a good example is salt, table salt, NaCl. Okay, now we said earlier that if we put different chemicals into solutions, even if they're not an acid or base, it can make the solution acidic or basic, right? So if I put salt, table salt, NaCl into a solution, it's going to break down into Na plus and Cl minus, right? And so the conjugate base that we have is Cl minus, right? Because it's the conjugate base of a strong acid. Okay. Now, since HCl is a strong acid, right? HCl is a strong acid. The conjugate base is a weak base, right? What that means is Cl minus is not going to do anything with water. It's not going to turn the solution acidic or basic. So not gonna make the solution acidic or basic. Okay, and it's because it's the conjugate of a strong acid. Okay, it's a weak base. It's not going to react with water. That's why we say it's just a spectator. It's just gonna float around in there. It's not gonna want to make HCl because theoretically, right, if we just kind of think about it, we can say, hey, Cl is gonna react with H2O and it can make HCl and OH minus, right? That's kind of the chemistry we've been looking at. But HCl is so strong, it's such a strong acid, it's always going to want to break apart. It's not going to want to form. So this reaction is never going to happen. And so Cl minus just kind of floats there, never fulfilling its potential of becoming a strong acid again. That's basically what this means. Okay. So the conjugate bases of a strong acid, they don't react with water, okay? They just kind of stay by themselves. Okay, and then if the acid is a weak acid, it's going to do the same thing that we looked at earlier. It's going to react with the water. It's going to form the acid again and go into equilibrium. Does that make sense? Hopefully. Sometimes I just look into your eyes and I just see hatred for Mr. O and for chemistry and boredom and sleepiness. Yeah, sleep is for the weak acids. Okay, So let's take a look at our first problem and let's think about this, okay? Okay, so here it's asking what effect will NO3 minus ions have on the pH of a solution? And what effect will CO3 2 minus ions have on a solution? Basically what this is asking us is, hey, if you put NO3 minus into a solution, what is it going to do to the pH? That's basically what it's asking. So NO3 minus is an anion, and so we need to look at its conjugate acid. What is the conjugate acid for NO3 minus? HNO3. Good. Super simple. Just need to add an H to it, right? Okay. Now, HNO3, is it a strong acid or a weak acid? Anyone remember? Strong. Yeah, it's very strong. It's stupid strong. It's a strong acid. Okay. So if HNO3 is a strong acid and NO3 minus is its conjugate, is NO3 minus gonna want to react with water? No, NO3 minus will not react with water. Okay, and it's because it's the conjugate of a strong acid. So will NO3 minus change the pH? No, no change on pH. Okay. Hopefully that makes sense. It's kind of the culmination of what we've been looking at. Again, the reason why this happens is because HNO3 is super duper strong. It's going to force everything into H plus and NO3 minus. It's not going to want to do anything. Okay. All right. So now that we did that first part, I want you guys to take a minute, not too long. You can talk with the person next to you. And I want you guys to tell me what effect you think CO3 2 minus will have on the solution. Is it going to make it more acidic, more basic, no change? Okay, take about a minute, and then we'll go over it together. All righty, guys, let's go over this one. Okay, so CO3 2 minus, what is the conjugate acid of this compound? Yeah, HCO3, right? So this guy is the conjugate base from HCO3 minus. Okay, so if we look at HCO3 minus, is that a strong or a weak acid? Yeah, this is not one of the strong acids, right? This is a weak acid. Okay, so if it's a weak acid, that means that the conjugate is going to react with water, right? And so what that means is CO3 2 minus is going to react with water, and it's going to turn into HCO3 minus plus OH minus. Okay, now, so if we think about this, let's just say, for example, hypothetically, our value right here is 0.1. If we set up an ice table, and you guys don't need to do this, how much of the products are we going to start with? 0. Okay. Now, are we going to gain or lose the base right here? Yeah, we're going to lose some, right? If we lose this, what happens to these guys? Yeah, we're going to increase. And so we can just stop right there. If CO3 2 minus reacts with water, the OH concentration is going to increase. If the concentration of OH increases, does it make it acidic or basic? Yeah, basic. So this baby right here is going to make the solution more basic. Okay. That's it. That's basically what we were talking about. You know, that long, all those paragraphs I had earlier, that's the application of that. Just keep that in mind. So you can actually go home, look at some of the household products that you have, and figure out if adding it's going to turn it acidic or basic. That's the first thing I did when I learned this. But I think I'm a little bit weird, so it's understandable if you don't do that. Okay, let's move on. Okay, so again, a lot more text, but let me just kind of break it down very simply for you. Okay, and you guys already know this. If Ka is bigger than Kb, the solution is acidic. If the Kb is bigger, the solution is going to be basic. We already learned this. I'm just kind of reviewing the information. Okay, now we're going to be talking about now the cation's ability to interact with water. Okay. Okay, so different cations have different Ka values. Okay, so you can see a table of this. And this tells you basically how much they're going to want to dissociate or break down inside of water. So just keep that in mind, that different metals, they can have different, different Ka values that tell us how much they break down. And same thing as before. The bigger the number, the more they want to break down. So Al is going to dissociate a lot more than iron will inside of water. That's basically what all of this is saying. Make sense? Okay. Now, there's going to be a combined effect when you have cations and anions in solutions, because if you have positive and negative, there's going to be some interaction there. Okay. So there's 4 possible combinations, and I'm going to do my best to kind of make this as simple as possible for you guys. Okay, so when we got a salt, okay, when we have a salt, it can either form acidic, basic, or neutral solution. And we have to look at what the cation and the anion do. So let's look at all of the combinations. Okay, if the salt contains an anion that does not react with water and a cation that does not react with water, we can expect the pH to be neutral. Okay. So let me just kind of write it right here. So if the anion, okay, and I'll write no reaction, and this is all talking about water, no reaction with water. And if the cation has no reaction with water, it's going to equal a neutral solution. And this happens when the anion is the conjugate base of a strong acid. And if the cation is in group 1A, or it's one of the heavier members of group 2A. Okay, so we got some examples right here. Now, if you guys notice, NaCl breaks down into Na plus and Cl minus, right? Cl minus is the conjugate of a strong acid, HCl. And if you look at Na, it is the conjugate acid of a strong base, NaOH. So there's the conjugates of strong acids and bases. Okay, we got another example right here, BaNO3 It's going to break down into Ba2 plus and NO3 minus. NO3 minus is the conjugate base of a strong acid, HNO3, and Ba2 plus is the conjugate base or conjugate acid of a strong base, BaOH2. So if you guys look back at your notes, you should see the strong bases and strong acids. So basically, if the cation is the conjugate acid of a strong base, and if the anion is the conjugate base of a strong acid, there's going to be no reaction, because neither of them are going to want to go backwards in the reaction. Okay. Okay, next we got salts that have anions that react with water and cations that do not react with water. So in this case, we have an anion, okay, that reacts with water, so reaction. And if the cation has no reaction, okay. Another way you guys can think about this is if the cation is the conjugate of a weak acid, and if the cation is the conjugate of a strong base. Okay. If this happens, it's going to make the solution basic, okay, because the anion will react with the water, making it basic, but the cation is not going to do it. Guys doing okay? I know this isn't the most fun part. Okay. The third possibility is if the anion basically is the conjugate of a strong acid And the cation is the conjugate of a weak base. It's going to cause the solution to be acidic. Okay, so basically the opposite of what we had in the previous example. So the first example, we had the conjugate of both strong acid and base, and that makes it neutral. Second example, if we have a conjugate of a weak acid and the conjugate of a strong base, it makes it basic. And then if we have the conjugate of a strong acid and a weak base, it's going to make it acidic. Okay. All right, and then the last one, you guys can probably tell what it's going to be. If the anion is the conjugate of a weak acid, and if the cation is the conjugate of a weak base, okay, in these situations, it depends. Okay, so it depends on the concentrations. Okay, so those are the 4 possibilities. I know that wasn't the most exciting thing, but just kind of had to go through them. But hopefully you guys have those down because we will jump right into a problem with that. Okay. So I'm going to show you guys how to do the first one, and then I'll have you guys do the other 2 parts of the problem on your own. Okay. Does anyone need more time to copy this down? Okay, yeah, I'll leave this up here for another minute. All right, I'm gonna go over the first part of the problem. Some of you guys might be able to do this already, so if you want to try all of them, go ahead and do so. But I'm gonna take it one at a time for everybody. Okay, so what we want to do is we want to figure out if adding these salts makes it acidic, basic, or neutral. So let's start with the first one. Okay, so one good way to do this is just to figure out what they break down into. So BaCH3COO2 becomes Ba2 plus, and then it's going to form 2 moles of the acetate ions, CH3CO. Okay, now we want to figure out what they're the conjugates of. So Ba2 plus, what is it a conjugate of? Yeah, it's the conjugate of a strong base. So it is a weak acid, but it's the conjugate of a strong base. Okay, so all right, it's the conjugate acid. So you guys were both right. There was no way to get this wrong, as long as you didn't say neutral. So it's the conjugate acid of a strong base. My fault. Okay, and the strong base that it's a conjugate of is going to be BaOH2. Okay. Okay, if we look at acetate, it's going to be the conjugate base of a weak acid. Okay, and the weak acid is going to be you just add an H to the end. Oh, yes, vinegar. All right, so if we look at this, is Ba going to affect the pH at all? No, this guy doesn't affect the pH at all because it's not going to want to go backwards to create the base. So the only thing that's going to affect the base or the pH is going to be this right here. So if it's the conjugate base of a weak acid, what does it turn the solution into? Acidic or basic? Basic, yeah, because it's it's a conjugate base. So if we have that, it's going to turn it basic. So this, if we add this salt into a solution, it's going to turn it basic. All right, any questions? Hopefully not too bad. I'm gonna give you guys about 3 minutes to try these out. Pick 2. Don't do all of them. I'm gonna go over all the answers, but just pick 2 of them. See if you can do 2 of them, and that should be fine. You don't have to do all of them, but I'll go over the answers for all of them. It's about 3 minutes, and then I'll go over them with you guys. Okay, so I'm gonna go through these really quickly. I'm just gonna give you the answers basically, and if you have any questions, please ask me during your break. Part B, it should be acidic. Okay. C should be neutral. Okay. And then D, you should have gotten acidic. And then E, you should have gotten basic. Okay. And if you want me to go over anything more specifically, we can do that during the break. All right, so we're gonna get started. We're gonna take our quick break. We'll take about 5 minutes. So if you need to go to the restroom, make sure to do so. Okay, just to reiterate to everybody, I made a mistake. Number 3, C is acidic, D is neutral, and E is acidic. Okay, my fault. Can't read. Okay, let's move on. So we're not gonna do this problem because I think you get the idea. We are going to skip all this right here. It's explaining why some chemicals are acidic and some of them are basic. You guys can do it in your reading that you guys all do. It's not that important, but we are going to go on to this part, which is very important. It's called the common ion effect. Okay, and we're going to end with this. Okay, and you kind of already know, or we kind of just talked about in the previous section. So you guys kind of have an idea of what this is going to be like. Okay, common ion effect is what the name sounds like. If you have a common ion, okay, so if you have an ion inside of solution already, if you add more of that ion, it's going to be affected by the ion that's in there. Okay, so let's take a look at an example right here. Sodium acetate. This is a salt, right? So let me draw a picture for you guys. Let's say that, for example, you have a container that you put sodium acetate into. Okay, so you got wrong one. CH3COONA. Okay, this is a salt. This is going to break down into a solution with the ions, right? So you'll have the acetate ion and you'll have Na+. Okay. This part makes sense, right? We've been doing this with the salt hydrolysis. Okay, now let's say that all of a sudden you were feeling very experimental and you decided to put some acid in there. Let's say that you put some acid. Now this acid right here wants to break down into H+ and CH3COO-. Okay, if you guys notice, you already have CH3COO- in there, right? Do you guys see that? Okay. So what this means is, since we already have some CH3COO-, if I add more acid, right? If I add an acid that has the same ion in there, what's going to happen is this acid, this conjugate base that's already present, it's going to affect how much this guy dissociates. So it's going to affect the dissociation. Okay. Okay. It's the chandelier effect, right? Or the chandelier principle. Because if I already have this, okay, and I try to add more of it, it's going to swing to the other side of the reaction, right? Okay. Since I have a lot of this already, it's going to make it so that this compound is going to want to dissociate less. It's going to break down less. Okay. So just to reiterate, this is the reaction between acetic acid, or the dissociation of acetic acid. if I got a lot of this, if I have a lot of this guy right here, the acetate ion, which I do because it's already in the solution, what's going to happen is it's not going to want to bring or break this guy down. So it's going to swing to the left. The reaction is going to shift to the left. It's the chandelier principle, right? If you have a lot of something on one side, it's going to shift it to the other side. So same thing here. The acetic acid is not going to want to break down as much because it already has a lot of the conjugate base on the other side. Okay, that's the common ion effect. So common ion effect is if you already have one of the ions in a solution, it's going to prevent the acid from breaking down as much. Okay, and so I summarized that section, that chapter for you guys, or that section. But if you want a better explanation, you guys can take a look at the book. It kind of goes into more detail. Okay. All right, and so we're going to close up today. I'm going to show you guys how this works in an ice table problem. Okay. But any questions before we do that? All right. Let's go to 12.50. Okay, so in this problem, it's asking us what's the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate. So I'm going to write the formulas for you. CH3, COOH, and sodium acetate, CH3, COONA, to make 1 liter of a solution. Okay, so there are a couple things we need to establish first. Okay, CH3COOH is a weak acid. Okay, it does not dissociate completely. Okay, and then CH3COONA is a strong electrolyte. Okay, which means it dissociates completely. It breaks down completely. Okay, so out of the two, sodium acetate gets priority. It breaks down completely. CH3 or acetic acid does not break down completely. So what this means is this guy right here is going to affect dissociation. Does that make sense? Okay, and it's because they both have this ion inside of them, acetate. Okay, so we don't need to write the reaction for this guy right here because it breaks down completely. What matters is going to be the acetic acid. So we're going to do acetic acid, CH3COOH, and it's going to dissociate into H plus and CH3COO minus. And we're going to set up an ice table. Okay, and if you don't get this completely, say don't worry, we will go over this when we come back on Monday. So don't feel too stressed. I know we're kind of rushing at the end here. Okay, now we need to start filling in our ice table. Okay, let's start with our acid. How many moles of the acid do we start off with? 0.3. And since it's 1 liter, we don't need to divide it, but I'm going to label it moles, okay? Now, usually when we start an ice table, we put 0 on top of both, right? But if you guys notice, how much sodium acetate do we have? We have 0.3 sodium acetate, which means since sodium acetate breaks down into Na plus and acetate, we're going to start off with some of this guy right here. We're going to start off with 0.3. We still don't start off with H plus, so we can keep that baby at 0. But we're going to start off with some sodium acid or some acetate in there. Dude, I'm getting the names mixed up. It's like potato, potato, tomato, tomato. But does that make sense why we start the ice table like that? It's because we start with some of the salt already in there. Okay. So from there, everything else is similar. The acid is still going to break down a bit, which means if I break down some of the acid, we're going to gain some of these guys right here. Okay. And so that means we're going to get 0.3 minus x, we're going to get x. And here we're going to get 0.3 plus x. I should have wrote the Ka. Okay, and then the Ka for acetic acid is going to be 1.8 times 10 to the negative 5. Okay, so from here, all we need to do is just plug it in to our equation, our Ka equation. So if I plug it in, I'm going to get Ka is equal to 1.8 times 10 to the negative 5. And so 1.8 times 10 to the negative 5 is going to equal, on the top, x times 0.3 plus x divided by 0.3 minus x. Okay. Okay, now, if you guys notice, what can we use to make the calculations easier here? 5% rule. Oh, praise God for the 5% rule. Because then we can get rid of the x here, get rid of the x here, and then this calculation becomes stupid easy, right? Okay, the 0.3 on the top, 0.3 on the bottom cancel out. And then the answer is x is equal to 1.8 times 10 to the negative 5. And then since we're looking for the pH, all we have to do is do pH is equal to the negative log of the concentration of H+. The concentration of H+ is x. We have the value for x, so we can just plug it into the equation right here. And I'll do the calculation for you. It's going to be 4.74. And that's it. That's how we would calculate the pH of the solution that already has acetate in there. If you guys wanted to test it out and set this to 0, you'll actually get a different number. And you'll see that the pH is going to change based on how much common ion you had in there before. Okay? Make sense? All right, so we'll stop right there. Thank you guys for bearing with me. We'll do a practice problem with this as soon as we come back. So don't feel super stressed out if you guys didn't get it completely. I did record this and I will be posting it, so you guys can review it if you want to. But next time we come back, we will be going over, start with the problem on common ions, okay?